Wind is a critical factor in driving fire behavior, but it's one of the most challenging weather elements to visualize. This presentation is going to use video to help you answer the question, can you see the wind? Remember that general winds are produced by high and low pressure systems, but only have partial influence on the fire. Their contribution is combined with local thermal winds to determine a location's 20-foot wind. Let's take a look at a video and identify a general and a local wind. You notice in this video, the clouds in the upper part of the frame are moving in a completely different direction from the smoke movement. Above the green line, we would consider this to be the general wind, and below the green line, a local wind. Local winds are driven by temperature differences typically associated with terrain. This fog video illustrates two of these local winds, upslope and up valley. Upslope and up valley effects can be going on at the same time in a given location. The typical diurnal cycle is for upslope winds to develop early in the day, and then generally up valley winds begin to dominate the entire mountain terrain system by afternoon. One important fire concern is the transition when an upslope changes to an up valley wind shown here in this video. So what happens during the nighttime hours? The slopes begin to cool and air begins to travel downhill. These downslope flows begin early in the evening, and then they begin to collect into the larger drainages, becoming down valley flows. And you can see in this video from Yosemite how the smoke is transported first downslope and then down valley. Normally we think a downslope down valley is quiet conditions because it's occurring during the nighttime hours. This next video illustrates how the transition to downslope can move a fire into unburned fuels. Fire activity was moderated by shading until the downslope winds began to develop. You can see mostly smoke coming up from the fire until the downslope flows begin to increase. The smoke is being bent downhill, and you start seeing more flames in the imagery. An even greater increase in fire behavior is observed as down valley winds develop. These down valley winds encounter the valley floor and cause an even greater increase in fire behavior. In this case, the early evening fire behavior was more dramatic than even the heat of day during the late afternoon. The main points to remember from this part of the presentation are that slope and valley effects can be observed at the same time, and your switch to downslope and down valley flows can actually be a time when you see an increase in fire behavior. This next case is an example of a general wind which occurs at night and can dramatically impact fire behavior. This is called the low-level jet, which is usually hundreds of feet above the surface fire. It works by not directly interacting with the surface fire, but providing a mechanism to enhance ventilation of fire columns, which in turn aids the surface combustion process by helping a flow of fresh air into the fire environment. The low-level jet is a critical wind over the plains of eastern Montana and Wyoming. It develops when an upper-level ridge causes hot weather west of the Continental Divide. The rising air associated with this heat is replaced by a fast-moving current of air over the plains. These winds, 1,500 feet above the surface, can be going at 20 to 40 miles an hour during the nighttime hours when friction is less. To illustrate the influence of the low-level jet on a fire, let's first look at normal nighttime fire behavior. This video shows that with an inversion in place, smoke is being kept over the fire, thus reducing the visibility. You can see the haziness. You can see the dramatic motion of the smoke columns in the video with the low-level jet. You can see that the smoke is being lifted away from the flames, causing good surface visibility. Remember, the actual low-level jet of 20 to 40 mile-an-hour winds is well above ground level, and you can see in the zoomed-in image that the smoke is initially rising straight up for a distance, indicating the good ventilation before the influence of the low-level jet is pushing the smoke from right to left in this image. The low-level jet is a critical wind across the plains of eastern Montana and Wyoming. It brings better ventilation to a fire during the nighttime hours, and many times it will bring a quick increase to fire behavior right after the heat of day when temperatures begin falling and humidity begins rising. Cold fronts are a critical wind that are a problem because their shift in the winds can often cause the flank of a fire to become a flaming front. Another weather problem associated with cold fronts is that the air mass becomes more unstable immediate to the frontal passage. This leads to an increase in fire behavior right before a significant wind shift. Observe the smoke column as you begin to see the lower clouds approach from the right, indicating the cold front's presence. The smoke begins to have much greater lift, indicating the air is becoming more unstable. This all occurs in this time lapse moments before the dramatic shift occurs with a cold front's arrival, driving the smoke from right to left across the picture. This is a key component of a cold front's danger, that it will see the air over the fire become more unstable, increasing fire behavior before bringing a dramatic push of wind. The stability of the atmosphere can be visualized using time-lapse imagery. Notice in this video that the fire columns briefly pulse up, producing a pyrocumulus cloud before sinking back down. It is the presence of a stable air mass that forces the smoke columns back down and also causes the smoke to linger at the lower elevations. You get the feel by watching this video that the presence of the stable atmosphere is keeping the fire from getting ahead of steam. This video demonstrates numerous components of a fire behaving with an unstable atmosphere. Early on in the video, you can see fire whirls occurring on the surface fire. You also may notice that the smoke moving up from the fire is rotating, indicating strong column growth. Looking further out, you can see that the columns are going to great heights, establishing a plume, and above the plume, in this unstable air mass, you can see cumulus or perhaps even pyrocumulus. We stress time and time again that cold fronts and their associated wind shifts are a major danger to firefighters. What can be just as important is the fact that the atmosphere becomes more unstable ahead of a cold front, which is a period of increasing fire behavior. The winds produced by mountain waves generate one of the 6 clouds of concern to firefighters, lenticular clouds. These are known as phone winds and are the result of strong winds running into mountains under a stable atmosphere. This forces the winds first upslope, and then they travel downslope as a strong, drying, and warming wind. We use the plural term waves because there are usually multiple waves present. In this video, you can see one wave breaking over the ridgeline, but there is also another wave closer to the camera. When mountain waves are present, you can assume eddies are being produced in the lee of the mountains. This means the winds will be erratic and bring sudden wind shifts in speed and direction. While this can impact the fire, the motion of these waves can even be down towards the ground, which is a particular hazard to aviation. The clouds produced by the winds containing this threat are called rotor clouds. Zooming in on an earlier clip onto an area we called Area 2, we can see that a rotor cloud is present in this location. And when we zoom in even more, we can see the rotating motion of this cloud. Rotor clouds can travel considerable distance from the location in which they form. It is really important to report the presence of rotor clouds to your aviation resources. Fire whirls develop under unstable conditions and create extremely dangerous situations. They are capable of producing significant spotting in all directions because of their violent rotation, generating local winds of 100 miles an hour or more. They also are an area of intense low pressure, which can cause strong inflow winds to develop on a day where winds had previously been light. Almost every fire column rotates, so you should expect erratic spotting and strong inflow winds anytime your fire begins to demonstrate strong vertical growth. Dust devils form under similar conditions to fire whirls and also cause erratic wind effects. Notice how the inflow into this dust devil is causing the winds to cross fire control lines. The large sagebrush make it easy to see the rotation around this dust devil, and as the dust devil nears active fire, it picks up smoldering sagebrush, causing spotting. These intense whirlwinds are extremely unpredictable and can actually spin in either clockwise or counterclockwise motion. When they develop, anticipating wind flows becomes impossible, and safety is your only concern. Remember that there are different types of wind, both observed and measured. Permanent weather stations measure the 20-foot wind, and those are the winds you will find in a planning and spot forecast. When you take a weather observation, that is more like a mid-flame wind, so the forecasters will estimate a 20-foot wind from your observation. I hope you have found this video about seeing the wind useful, and it helps reinforce lessons from your fire behavior classes.